These are your 7-6 growth and decay notes. In this section, we are going to talk about word problems that involve growth and decay. Both represent exponential functions. So we have 3 formulas, and I have an example for each of the 3 formulas. So in your classwork, you're going to have a word problem, and then you have to decide which formula applies. It's pretty simple. If you're going to have exponential growth, you're going to be looking for things that maybe grow or increase. Maybe you'll recognize that the number's increased. So look for clues in the words that represent that the new amount will be greater than the old amount. Here's the formula for growth. You have y is equal to a times the quantity 1 plus r raised to the t power. And each of these things represent something different. Your a value is the initial amount. That's what you began with. So maybe when we talk about growth, maybe we're talking about an initial amount of bacteria in a petri dish. Maybe there were 100 bacterium. Maybe it's $100 in a savings account. It's whatever the initial amount was. Maybe there's 1,000 people, and then the population grew. Your y value is the new amount. So after you calculate all of these things with the a value, y will equal the new amount. So we take the initial amount and we multiply it by the quantity 1 plus r to the t value. The r value is the rate of change. It's expressed as a decimal. It has to be positive, greater than 0. So your rate of change, whether you are growing or decaying, it's always a positive amount. But I do want to mention that if you had a 34% rate of change, whether it was growth or decay, you have to move it over 2 decimal places so that we can actually use it to calculate. It's like dividing by 100 because percents are always out of 100. So if it was 34%, it would be 0.34. You have to be careful. Sometimes rates of change are decimals themselves. So 2.5% rate of change, you still have to move it 2 places. So you'll get 0.025. So always, when it has a percent sign, or they talk about a percent or as a rate, you have to move the decimal 2 places. It's like dividing by 100. Every percent is out of 100%. The t value, the exponent that you're raising that quantity to, is time. And depending on the problem, it could be time in years. You could be counting decades, so every 1 would be 10 years, 2 would be 20 years. Maybe it's seconds. In terms of bacteria growth, it could be minutes, it could be seconds, it could be hours. So you just look at the problem and you apply the right time, units of time to that problem. So let's use this problem, this equation, to answer these 2 questions, 2 parts of this question. Our first one has to do with population. So in 2008, Flat Rock had a population of 280,000 people and a growth rate of 0.85% per year. So they want us to write an equation of this information, okay, and it has a growth rate. So that was our clue that we're going to use the growth formula. We have 280,000 and we have the 0.85. They didn't give us a year, but they just said per year. So now we know our units of measurement. So to represent this in an equation, the 280,000 is A. That's our initial amount. This is my R value, but I'm going to have to change it to a decimal. So it's 0.0085. And then my years will just be T right now, time in years. And then as we get into more detail, like in part B, we can apply the years that we need to. So we're going to set up an equation. My new amount, Y, will equal the original amount, 280,000, times 1 plus 0.0085 to the t power. Now you have a formula that you can use for 10 years, for 20 years, for 1 year, however many years you want to apply this data. So now that I have my formula, I look at part B, and part B says, according to the equation, what will be the population of Flat Creek in the year 2018? Well, since my equation is based off of 2008, in 2018, 2018, my time t will be 10 years. And so I'm just going to take that same equation, y is equal to 280,000 times 1 plus 0.0085 to the 10th power. You could plug all of that in exactly the way it's written. Your calculator will know to apply the 10th power to this quantity first, then multiply by the 280,000. If you want to do it in parts, using the order of operations, you need to combine this 1.0085, raise it to the 10th power, then multiply by 280,000. But I really think just plugging it into your calculator the way it's written will be the easiest way with the least amount of errors. And so my new population in 2018 will be 304,731 people. Now, I'd like you to pause right now, try that with your calculator, and make sure that you get that same calculation. And if you don't, we need to figure out how to use your calculator. Okay? So that is growth. And just as a quick check, my new answer is larger than my original answer, and that's a good thing. That means that it did grow. For decay, we have another formula, very similar to growth, which is nice because there's really not a whole lot of change other than the fact that rather than adding the rate of change, we are going to subtract the rate of change. So a couple words for decay. Obviously decay, that means something is going down, decreasing, and sometimes we call that depression or recession, that things went downward. And so again, the A value represents the original amount. The Y value is the new amount after all these changes occur. The rate is the rate of decay expressed as a decimal. And they're telling you there that the R value will be a proper fraction because it's going to be smaller, but it could also be, rate of change can be, it just has to be a fraction and positive. T is time once again. So looking at example 2 here, during an economic recession, that means when times are bad, the prices of things are dropping down, quality of homes and things are going down. Things that are worth money are actually losing value. A charitable organization found that its donations dropped by 1.1% per year because people's pay goes down in a recession. So people aren't going to be giving to charitable organizations as much. So the donation amount dropped. This is a decay. Before the recession, its donations were 390,000. So this is my A value, my original amount. This is my R value, but I'm actually going to change it to 0.011. Had to move the decimal 2 places to the left. And so we're going to again write an equation based on T amount of years. So Y equals 390,000, my original amount, times the quantity 1 minus 0.011 to the T power. If you plug that into your calculator, you should just get the exact value when we change it to 5 years. So the only thing we have to change now is replace the years with 5 years. And we are talking years, not minutes or not hours. And when you plug that in, as long as you did all of your math correctly, in 5 years, based on this decline, they will have only had donations of $369,016. I know 74 cents would be what you'd round to because it's money. When we're talking about that much money, we usually just round to the nearest whole dollar. But either or. And just as a quick check, we make sure that the new amount is smaller than the original amount, and it is, and that shows decay. The last equation I want to expose you to involves interest. Interest is a good thing, or it can be a bad thing. It depends. Compounding interest is when people pay money on money borrowed, or the bank pays you money for borrowing your money. So it can be good. If you're putting money into a bank and investing money, the bank sort of gives you a thank you by giving you extra money on top of it, a percentage, as a way to say thank you for allowing us to use your money to help the bank survive. If you have a credit card, the credit card charges you interest, so you're borrowing their money to pay for something, and you don't have the money, so it's sort of a fee to say, well, we're allowing you to borrow it, so if you borrow $100, we're going to charge you $105 or $120 because you didn't have it, so it's going to cost you a little bit more. So it can go both ways. When you compound interest, it's how often you look at the interest and how often the bank says you have to pay them that extra money, or how often the bank is going to pay you. And so it has to do with compounding times. So let's just quickly go through this. It's very similar to growth. Your p-value is in the spot where the old a is. That's your principal amount. Principal means it's your initial amount. So a lot of times when we're talking about money, they'll talk about principal amount rather than original. Your A is the current amount after after the interest has been included. Your R value is that rate, again, as a decimal. And the N value is the number of times it's compounded each year. And we're going to compound per year. So when you compound things, I have my little compounding times. If something is said to be compounded annually, that means that the bank is only going to look at your account one time a year, and based on the amount of money that you had in there, they're going to pay you interest on it. Just once a year they're going to look. Semi-annually, that means twice a year, every 6 months. Quarterly implies every 3 months, 4 times a year. Quarter is 4. Monthly, every month, they're going to look at the amount of money that you had in your account, and they're going to pay you money on top of it for allowing you to borrow it. Or a credit card is going to look at that and say, oh, you borrowed $100 this month. This is now your interest, how much you owe. And then it compounds, because now the next month, not only do you have the money you borrowed initially, then you have the money that you owe from the interest, and so it can get a little scary as far as paying back a credit card. But it works good, and it works for you when it's the bank doing it. Weekly means every week, 52 times per year. They're looking every week. And then daily. Daily would be 365. Now there's continuous compounding, and that you'll approach when you get into some of your higher level classes. It involves a more complicated formula. Okay, so we're going to use this formula to calculate a college fund. Okay, so when Paige was born, her grandparents invested $1,000 at a fixed rate of 7%. So the $1,000 is the principal. That's how much they invested. The 7% is the rate, your R value. And this is the other clue. It's compounded annually. So that means my N value is 1. It's not going to change a whole lot of things here. Paige will receive the money when she turns 18. That is your time in years, after 18 years. So what amount of money will Paige receive from the investment? So we set up our formula. A is equal to P times 1 plus R divided by N all over N to the T. So A is equal to $1,000 times the quantity 1 plus 0.07 divided by 1 raised to the 1 times 18 power. If it was semi-annually, we would divide by 2, and then we'd have a 2 up in the, we'd have a 2 here and here. If it was quarterly, we would divide by 4, and we'd have a 4 up there. And when we plug this into our calculator, you just have to be careful that when you do plug in the power that you're raising it to, you might want to use parentheses around that, or just do the math. 1 times 18 and just plugging in as 18. When it's all said and done, without adding any more money to the account, okay, just based off the $1,000, after 18 years, she will have $3,379.93 in her fund, which is telling us that the bank paid her a lot of interest just for letting her borrow the $1,000. And so it kept growing and growing and growing. So, real quick, summarizing your own words what this lesson is about. If you have a question, you're more than welcome to say it there. on anything, maybe the rate or compounding. And then here's your practice problem. Last section of notes for Chapter 7.